Hello and welcome to the Actian Hybrid Data Conference breakout session, Better Together Avalanche 2.0 in Google GKE. My name's Jeremy Hankinson. Okay, so what we're going to talk about today is how Actian Avalanche was re-architected using GKE and cloud-native storage to provide or to produce a highly performant, scalable and more easily manageable product. We're going to start with a little bit of a history lesson, an overview of the origins of Avalanche, and then take a look at the architecture for Avalanche 1.0. After that, we're then going to look at some of the limitations that Avalanche 1.0 has, and then dive into how these were improved during the re-architecture using containerization and GKE and cloud-native storage. And then we'll circle back to see how these changes have affected the architecture for 2.0. And then we'll spend a bit of time summarizing the benefits of these changes. And then finally, we'll come on to my current conundrum in performance engineering. Some of these changes have showed results that we didn't quite expect, so I'm going to spend a little bit of time talking about that. And then where can you go next to get more information? Avalanche is based in an on-premise product called Actian Vector on Hadoop. Actian Vector on Hadoop is an MPP analytics database that consists of a leader node which receives the queries and prepares them for processing. They're then sent out across the cluster for execution across all the nodes, and the results are returned to the leader node for returning back to the client. The storage for this product, as the name suggests, is Hadoop HDFS. Each of the nodes in the cluster has its own locally attached storage, which is used with the addition of an HDF name node to produce an HDFS file system, which is accessible to all nodes of the cluster. This architecture suits itself quite well for moving into the cloud, which is how we came up with the architecture for Avalanche 1.0. which we see an overview of here. In this setup, the individual nodes in the cluster are represented by virtual machines or cloud compute instances. Each of those instances have their own attached storage in the form of provisioned SSDs from the cloud provider. And that, along with a name node VM and some other supporting services, generates is used to produce the HDFS file system, which is used for storage across the cluster. Then that's made public to the outside world over ODBC and JDBC and our regular client tools, over an encrypted HTTPS channel, and by default, no one's allowed to connect, obviously, and access is granted via an allow list. So this is a sort of high-level summary of the architecture for Avalanche 1.0. It worked fairly well for us, but there are some limitations on it, which we're going to dive into a little bit now. Firstly, it was pretty slow to deploy. Each of the individual nodes of the cluster have to be deployed separately, and then each individual component has to be installed and set up independently, leading to an over 30-minute window to deploy the cluster for the first time. It also led to fairly significant restart times, often over 10 minutes. Also, because the network bandwidth is tied directly to the underlying architecture, so the underlying hardware, this resulted in reduced network bandwidth for smaller clusters, which in turn could reduce performance. Secondly, these are very much static deployments because of the way they're built up. Once they're deployed, patching and upgrading has to be done on an individual component basis. The updating itself has to be done manually. We couldn't automatically roll out fixes when they were available. Clusters had to be individually updated. And for the same reason, it also made it very difficult to push out new features to existing customers, to existing clusters. It wasn't impossible, but it was a manual process and was generally done on a request-only basis. And then finally, the architecture itself, the environment, doesn't implicitly support self-healing. If we lose a node because of an underlying failure in the compute instance, because the cloud provider has an issue, the cluster will just fail and doesn't have any ability to restart or reheal, and so that would have to be dealt with manually. And then finally, the architecture itself is dependent on HDFS. HDFS uses provisioned storage, and in a cloud environment, this is a very expensive way to go. There's a fixed amount of storage per node, which means your total amount of storage is limited by the total number of nodes in the cluster. You may require a capacity of, let's say, 16 terabytes of space. So if we have 4 terabytes per node, then you're going to need 4 nodes. But your compute resources, your compute requirements may only be 2 nodes, but you don't get that efficiency because you need the 4 nodes to supply the storage. The other thing about provisioned storage, as I've mentioned, is because it's provisioned when it's attached, not when it's used, you're paying for the full amount whether you're using it or not. And then finally, HDFS is difficult to scale, certainly automatically. Adding new nodes is a complicated process, and often for optimal performance, the data needs to be co-located with the node that's processing it, so we need to get into data movements. So there are a number of issues that became apparent in Avalanche 1 that needed addressing. So we're going to look now at a little bit how these, how we address these for Avalanche 2.0. So first of all, we're going to take a look at the deployment changes. So in rearchitecting for Avalanche 2.0, we took advantage of containerization. And you can think of containerization as the next step in the evolution of deployment. If we think about Vector on Hadoop as an on-premises solution, generally the way this will be deployed is on a fixed piece of hardware. You deploy the hardware, you deploy the operating system, and then the application sits on top. This works fairly well for deploying the application, but it's a very static use of resources. Whether you're using the cluster, whether you're using the hardware at full capacity or not, it can't be used by anything else. It's either running or it's not, but it has one use, and that's the use that it was assigned to. As we move into Avalanche 1.0 and in the cloud, we see a virtualized environment where you have a single piece of hardware and an operating system, but then a hypervisor sits on top of that, which allows you to run multiple virtual machines on the same piece of hardware. What this means is that you can use one piece of hardware for 2 or 3 or maybe more application stacks, each running their own virtual operating system. And when one is down, the other one can be up. And so the resources can be shared for multiple purposes. But each individual instance is still running its own operating system. So it's not the most efficient use of the underlying resources. There's certainly a amount of duplication in management, which maybe doesn't need to happen. That brings us on to Avalanche 2.0, which uses containerization. Now, the architecture is fairly similar here. We have the underlying hardware host and then an operating system. And then above that, we have a container runtime. The container runtime allows us to deploy these reduced containers containing only the dependencies of the application and the application itself. There's only one instance of the operating system running, which is a much more efficient use of resources. So what exactly is containerization? By definition, containerization is virtualization at the OS or software level. Multiple containers deploy on a single OS host, giving the most efficient use of resources. The kernel in the operating system supports isolation through namespaces where the containers get deployed. A virtual machine architecture is generally seen as virtualization at the hardware level as opposed to software level. Each application in a container is packaged with all its dependencies in a self-contained image. It contains only those requirements to run the app. It doesn't need a full operating system. And this in turn makes it a lot smaller than a typical virtual machine image. Usually they're only up to a few hundred megs in size. And because you're deploying a pre-built image into a runtime environment, it's actually much more straightforward to deploy and often quicker to start up. You're not starting a full operating system. The host is already provisioned. You're really just you're deploying an image into a runtime, which improves deployment, which improves ease of deployment. And then particularly usefully, the images themselves are versioned. This allows for source code level tracking in what the images contain. Every time you build, pull in differences, you bump the version number, and you can tell very easily exactly which versions of any particular application that a specific image is running. And then finally, the platform most popular for this at the moment is Docker. We use Docker extensively in Actian for both Avalanche and other products. So once you have your containers, once you have your images, how do you deploy them as containers? The infrastructure we use for deploying the containers is called Kubernetes. Kubernetes is an orchestration tool for containerization. It has a number of different roles. It provisions underlying hosts, storage, and the rest of underlying infrastructure for running the containers, everything else. And it also provides a mechanism for running and monitoring workloads, setting policies, managing security, managing sensitive information. So it covers absolutely everything to do with the deployment of the containers. Containers in Kubernetes are deployed as pods. Pods are the smallest unit of compute resource in Kubernetes. You can think of it as analogous to an individual VM, except the main difference with a pod is that it can run multiple containers, either concurrently or as is particularly useful for deploying a multi-pod cluster for initialization. You can launch short-lived containers to help with scheduling, ordering, waiting, and pre-setup, and then finally deploy your runtime container when the system's ready to go. And all these containers share the same resources in the pod. So the same things are available to the init containers to the main runtime container. Now, all this is a lot of information, a lot of things to configure, and the way Kubernetes handles this is with YAML files. Every single resource that's deployed within Kubernetes has to be defined using a YAML file. Even with fairly simple applications, when you're talking about storage, image, maybe network infrastructure, permissions, you can very quickly have to deal with a lot of different YAML files, and it gets very complex very quickly. The way we've dealt with this, and is quite common, is by the use of Helm charts. And Helm charts are used to simplify the generation of the YAML by using templates. This allows you to specify fairly easily the images, resources, dependencies, network topologies, and anything else that's required for your application to deploy successfully in a single self-contained unit. All those individual pieces are tied together in one individual component, which allows for ease of deployment. And similar to images, Helm charts are versioned. So again, you have very tight control of what's being deployed, what versions of each individual component are deployed within the Helm release. And so that in itself helps with versioning. Inside the Google Cloud infrastructure, the Kubernetes is available as part of GKE, which is the Google Kubernetes Engine. GKE uses node pools to provision hosts. Node pools are essentially groups of the same class of underlying host on top of which the pods run. The node pools support auto-scaling and load balancing. They will auto-scale up to 15,000 nodes, depending on your resource requirements. As soon as the current nodes are overloaded, new ones are spun up very quickly. And also critically, they will scale back down to 0 once the resource is not being used anymore. And this is a huge cost saving. There's an easy way to implement cost saving. Your resources are only there when they're being used, and they're gone when they're not. It also supports auto upgrade of the Kubernetes infrastructure, self-healing. If one node goes down, Another one is automatically spun up, and the pods are migrated over towards the new node. And this all happens as part of GKE. There's nothing we really have to code around it, to take advantage of. Obviously, there are some things we do to make it happen more smoothly for our particular use case, but this is available from the environment from the start. There's a huge range of compute options available, which allows us to have large, high-powered node pools for the warehouses, and smaller ones for the microservices and support around it, which gives us a very efficient use of resources. They also offer zonal and regional redundancy. And critically, for me at least, for my department, it makes experimentation very easily. We can create node pools with different configurations, different ratios of compute resources to RAM, and we can just set them to 0 or leave them to idle when they're not in use. We're not charged for them, but then we can just choose the class we want to deploy on when we do, and they'll spin up without any further configuration. So that's the compute instance re-architecture. What about the storage? Let's take a look at that next. So in the move to cloud-native storage, we were able to address a number of things. So initially and crucially, it allowed us to remove and replace the HDFS infrastructure. This meant that we could remove Hadoop completely, which freed up the resources that were consumed by it, which allowed us to allocate them directly to the warehouse, and also it improved I/O performance. So the way this works is that the data is stored directly in the cloud storage buckets as blobs. In a blob and a bucket environment, it uses an eventual consistency model, which means that changes you make to files, deletes, etc., won't necessarily manifest immediately. So to get around that, we switch from a multiple write model to a write once model. Which means any data that's written is immutable, and if it needs to be changed, then the blocks are rewritten. The advantage of this environment is that you only pay for the storage that you used. When you create the bucket, there's no cost associated with it. It's only once you start adding data to it that you start to accrue a cost. And it can scale effectively infinitely. And this meant that we can remove the vast majority of the locally attached storage from the clusters, passing that saving on to the customers. And then finally, it's allowed us to implement separation of storage and compute. What this means is that you're now able to scale compute resources independently of storage. The deployment can be based entirely on your current need, and there's no need to provision for peak usage or a particular amount of storage. So let's look at how that might work in a little more detail. So here we have a cloud storage bucket, and let's say we decide we want to deploy a 2-node cluster to do some work. We're going to create a table, and the way data is distributed in vectorwise in Avalanche is by use of partitions. So we're going to choose 8 partitions for this particular table, and they get allocated dynamically based on the topology of the cluster. So the first 4 get assigned to the leader node, and the second 4 get assigned to the worker node. So now we have our table. We're going to enter some data into it before we run our queries. So we load the data, and it's automatically distributed across all the partitions in the cluster, allowing for easy, even distribution. Now we've got some data on our cluster. We run some queries. We're happy with our performance. So we keep going, and we load some more data. It's distributed in the same way. Half the data is allocated to the first node, so half the data gets allocated to the second node. And now we're noticing that maybe we don't have enough compute resources to get the performance we're looking for. So at this point, what we can do is restart the cluster to give us more compute resources without touching the underlying data. So we restart our 2-node cluster with a 4-node cluster. As the data comes up, the partitions are dynamically allocated based on the new topology. So the leader node gets the first 2, the first worker gets the second 2, and so on until all the partitions are allocated evenly across the cluster. We can now run our queries again with the benefit of extra compute resources, having not had to touch our data at all. Okay, so how have these changes affected the architecture of the architectural view of the product for Avalanche 2.0? Well, it looks fairly similar to the architecture for 1.0. We still have the same allow list access over encrypted HTTPS channels. We still have ODBC, JDBC as we would expect. The main difference here we can certainly see in the deployment is that we now have a GKE cluster sitting underneath everything. Within that, we have two node pools, a higher spec one for running the warehouse resources, and then a lower spec one for running the microservices which support the cluster. And then on the storage side, we still have a small amount of provisioned storage attached to the leader. This is essentially for local metadata that allows us to keep track of stuff locally. And then, but all the main storage, the data storage, is now in cloud storage. And that obviously persists beyond the life of the cluster, so we can start up and shut down as needed, and not worry too much. Not worry too much about what the topology of the cluster looks like when it next comes up. We know that it's going to be able to make optimal use of the resources we have. So, what has this re-architecting given us? Well, primarily, or not primarily, but firstly, it greatly reduced deployment time. As I said initially, the AV1 had a deployment time sometimes well in excess of 30 minutes. That's now down to about 4 or 5 minutes, depending on the cluster size and the time it takes for the underlying nodes to start up. But 4 or 5 seems to be about average for that. Secondly, it's given us a rolling update stream. Thanks to the benefits of containerization and Kubernetes and the tools involved in that, we now have a well-defined versioning for each deployment and an automated mechanism for deploying fixes to all components in that level. That means that fixes can be pushed out to clusters automatically without customers necessarily having to request them, and critically without DevOps having to go and manually deploy them. It's also given us a very good mechanism for deploying new features. That means that existing clusters can be upgraded over time without the need to manually install them, or without the need for customers to create new clusters to receive them. We now have infinitely scalable storage. You're not confined by your compute resources in the amount of storage you have. You just create the cluster and load data as you need, and then scale your compute resources up to match. This as well gives us independently scalable compute resources. As I said, if you need to scale up your cluster because of increasing data volumes, or just because you need to run some reports at the end of the quarter, which requires more resources, you can easily do that for the time you need it and scale back as when you don't. And it's given us a vastly improved infrastructure. It's now more scalable. The performance over AV1, for our usual performance metrics, we've seen an over 30% increase from AV1, and that's with hot queries. So most of the data was already in RAM. For I/O, we've seen sometimes 2 or 3x performance depending on the application. We now have a much more self-healing environment. Obviously, it can't deal with all failures, but if we're certainly much more fault tolerant. Any failures in the underlying infrastructure automatically initiate a restart. The pods can either be rescheduled automatically or in a very short space of time afterwards. And from a development point of view, the environment is now vastly more portable. Kubernetes is a generic open source environment. It's implemented by all the cloud providers. It's also available on premises. And so if we wanted to deploy this in the other cloud providers or on premises at some point in the future, we're not having to move the entire environment, port the entire environment soup to nuts. We just have to deal with the local variations for that particular implementation of Kubernetes, which makes things generally more scalable. And then finally, although I mentioned that we've done comparisons with AV1 versus AV2. AV1 itself deploys in a different cloud provider. It uses different instance classes. So comparing them, comparing the two isn't quite comparing apples to apples. And in performance engineering, we like to be able to compare very specific features where the rest of the environment is stable. So what we wanted to try and do was look at the performance benefits of moving from HDFS to cloud native storage. We don't really take into effect the other benefits such as scalability or cost. We just want to look at raw performance. And the way we did this was using the TPC-H benchmark at the scale factor 1000, which uses 1 terabyte of data. We use it without the indexes because what we're interested really in is raw I/O performance, not analytics performance. We set up 2 identical clusters, one that was using HDFS for storage and one that was using GKE. What we found, which matched what we expected, was that for the hot runs where all the data is already in memory, we saw a roughly 5% improvement in performance. Not a huge amount, but quite a lot just from changing the storage backend. And this is largely attributed to the extra resources we have. But interestingly, when we looked at the cold runs where all the data is being read from the storage before the queries can be run, HDFS in this environment with the local provision storage actually performs significantly better. Now, this was surprising because in a lot of the other testing we'd seen the I/O with cloud native storage was significantly higher. We've been working actively with Google to investigate this. They've been a great engaged partner. And I think what we're actually seeing, if we can look at the numbers just down below slightly there, I'll highlight them. Yeah, there's a roughly 40-second differential in performance. Sorry, a 40% differential in performance between the two environments. And it seems that the Google infrastructure with the provision storage is sufficiently high performance that we get incredible throughput from the provision storage, which although the cloud native storage is very high, the local is even higher. And I think what we will do is use this to take advantage of some sort of local caching in the future so that the cloud native storage can also benefit from this performance. That's just about all it is from me. All that remains to say is if you're interested in the presentation, you want more info, you want to try out Avalanche 2.0, the best thing to do is go to the Google Marketplace where Avalanche 2.0 is now available. If you're interested in more information on GKE and the environment we're running in, you can follow the link here to get more information on that. Thank you very much for attending. I hope you enjoyed it, and please feel free to email me directly if you have any questions.